Let's get started. This is the NMR sheet, blue sheet. Any questions about this so far? I put this together to help kind of guide you a little bit as you're working through the chapter. In about a week and a half or 2 weeks, we're going to come back and finish up NMR, and we'll do it boom, boom, boom. Don't wait till then to be doing some things. Everything we covered in the handout needs to be solidified. You need to be looking ahead. A couple of these questions are getting you to look ahead a little bit. I noticed at the very first question you need more information. More information is needed. We got to give you that. Add to that. This is let's say you're using a 300 megahertz NMR. Number one. That essentially refers to the strength of the magnet, but that's not in Tesla. That's actually the frequency for the proton signals. You need that information. You should be able to find out how to do this in the book, the chapter. It's getting at what does ppm mean? What does parts per million mean? Okay, in terms of NMR. Please be looking at that, ask any questions in class, etc. There any questions about lab today? Sarah?
Do you have to be familiar with that chart? Like how you would have to reference it?
Maybe afterwards. Some familiarity with it, but not really detailed. Basically, the important thing is getting the suction on. It's very scientific. Using your finger, you don't want the hose to stick to your finger. If it sticks to your finger, it's going to be too strong. You're okay otherwise. Questions?
Are we doing C in NMR?
We probably are not actually going to run the carbon NMR. By the way, carbon NMR takes overnight, so I mean, unless y'all want to stay here overnight, but I'll probably pass it out. But yeah, we'll use carbon NMR to determine the product. Matt?
How do you use this SciFinder database?
There's instructions in the workbook. Do you have questions about the instructions? Okay. Question?
I couldn't find like storage and like.
You can find what?
The storage information and like safety data on SciFinder. Can I go to like
Storage information?
and for the lab day?
Okay. No. Hopefully it says in the directions in the workbook. Safety information can come from anywhere.
Okay.
Yeah. Safety information can come from ChemExpert or wherever any open source. SciFinder is mainly going to be for boiling points, melting points, where you want primary literature. And I'm not requiring that for safety. Okay. Good questions. We'll look back. I don't suppose we need to go further back than paclopyridine. Was there anything we didn't do before, right here? Paclopyridine, good way to eliminate or dehydrate an alcohol by what type of mechanism? E2. Pacl activates the OH, a lot like a tosyl. But at the same time, the pyridine that does the E2, it is strong enough. Product here. I'm just going to kind of get to an intermediate. You can do the full mechanism. This gets on the phosphorus. We end up with something like this. Yeah, we can show a mechanism for that. This can then eliminate. We'd like to put the double bond in here. You'd like to get the Zaitsev product. Double bond here would be more substituted, right? Boom. We're eliminating water. We're dehydrating. Alkene. Boom. This is the Zaitsev alkene. Where we remove this H and the leaving group. We could also maybe remove one of these H's theoretically, and that would give the double bond up top here. Nothing would happen to that stereochemistry there. Zaitsev, what's that, Hoffman? We'd like to form this, but E2, we're doing E2 here, has a stereochemical requirement. The hydrogen, the beta hydrogen in the leaving group must be anticoplanar, or transcoplanar. Is that H in this leaving group, first off, trans? Yes, they're trans. This is a dashed H, that's a bold O8. They're trans on the ring. It's easy to see in rings. And actually with a ring, that's all you need is trans. Because they will be coplanar if you do a chair conformation. By the way, for these to be coplanar, does the leaving group need to be axial or equatorial? Axial. Okay, but that's different. Here, these are trans, boom. Pyridine takes the H, electrons move in, kick off the leaving group. What do we get? We get that product. It's not going to take the other H, give this product. This is a more stable product, right? In terms of energy. And thus, we kind of assume that the transition state leading to this product is going to be lower than the transition state energy leading to this product. Basically, that's it. How about the next one, though? It's the same exact thing, except what? The methyl is dashed, and so the H here is what? The H is bold. Here, when this gets activated, I'm not going to redraw it, okay? The POCL. Is the beta hydrogen in the leaving group trans? No. Well, then guess what? They then are not transcoplanar. Have to first be trans. Okay? It could be ciscoplanar, but guess what? There's two H's up here. One is bold, one is dashed. Is one of these H's trans? Yes, HA. All right, I'm going to have to put the P here so it doesn't look like we're eliminating an OH. The pyridine takes this H, these electrons move in, kick that off. Because that H in that leaving group is trans, ultimately it will be transcoplanar. And what do we get there? We actually get this other, hold on, it's going to be dashed. Let's redraw it here. Double bond there. Nothing happened down here to that methyl. That methyl is still like that. Of course, the H is still bold, but I'm not drawing it. And if we call this H A and B, what H remains there? Yeah, B. So which H gets subtracted? Okay? So this is the case. Why would it go this way? Because this way you get to do a transcoplanar elimination. And even though it gives the Hoffman product, transcoplanar is highly preferred than ciscoplanar. Basically always do a transcoplanar preferentially. So the top one gives the Zaitsev product. The bottom one gives a Hoffman product. Stereochemistry there. By the way, I see a lot of students who want to draw this methyl bold. We call this bold there. Why is it not bold here?
It's no longer SP3.
It's no longer SP3. It's now SP2, trigonal planar. Everything's in the plane. Nothing's forward or back. It's in the plane now. Hopefully this is reviewed. E2, you have to keep in mind the stereochemical requirement for the elimination. Anticoplanar, highly preferred. Questions about these?
Why didn't you draw the Hoffman for the left of, why is that one on? Is that one actually missing?
This here? Well, coming this way, this is the top reaction. This was if we took one of these H's. I just showed it to, I mean, that's the product for the top reaction. That's a theoretical, for the top reaction, this is a theoretical Hoffman.
It doesn't actually.
No, because you'd rather make the Zaitsev. I mean, one of these H's is trans, one of these is cis. Which H? You have two options. Would you rather take this trans H or this one? Well, you'd rather take the one that's going to have the lowest transition state energy. The lowest transition state energy is going to be the one that gives a lower energy product. If you have an option, you got to look for something else to decide. Here we didn't have an option. We had to make the Hoffman. Okay. Did we answer that one in class? I think we did, didn't we? Here's that D. Williamson ether synthesis. I think we did that one. Did we do a synthesis of this guy? Ethyl phenyl ether. Show Williamson's ether synthesis. I'm going to go backwards, retrosynthetic arrow. I could break this apart over here. A. That is an O minus attacks a carbon. An O minus attacks a carbon. Do I just want it to attack ethanol or ethane? No, what's got to be on this carbon? A leaving group. What's your favorite leaving group, Doug? BR. I knew you were going to say that. There we go. We could go back and propose that reaction. Would that reaction give that product by what mechanism? SN2? So coming forward, would that give an SN2? I mean, would it give that product? Yeah. It should. We can also maybe propose, at least theoretically, making the oxygen carbon bond on the other side. Call that B. We break that apart into this O minus plus what? A benzene ring with a leaving group. And we'll stick with Br. If we had those, would that give this? No. And if it would, what mechanism are you proposing? It would not, because the only substitution mechanisms you know, well, you now know 3, addition and elimination. You don't do any of those on this. You don't do SN2 or SN1 on a trigonal planar carbon. SN1 and SN2 only occur on tetrahedral carbons. We'll learn later that you can do an addition elimination here, but not unless there's something else on the ring. Basically, you cannot do this. This mechanism will not work. Williamson ether is usually a good old SN2. Thus, the leaving group needs to be on one type of carbon? Tetrahedral. Again, we'll discuss this during test 2, how we can actually do that, but it needs some changes. So which way you want to do, A or B? Duh. A. Now, let's go back to original starting materials, or neutral. I mean, this is not really neutral. I would want you to go back here. How do you make this? Well, you make that from the OH compound, right? Let's go back to here. Neutral compounds. How do you go forward? What do you react this with to get the phenoxide? Dominique? NaH would work. That's like killing a mosquito with a bazooka, though. It's only needed with a regular alcohol. This is a phenol, much more acidic. We can use a weaker base, one that's not as flammable, one that's cheaper. How about just sodium hydroxide? Will sodium hydroxide be protonated phenol? Yes. pKa water 16, phenol is 10, difference of 6. That equilibrium lies in your favor by 1,000,000. So, deprotonate the phenol, make the phenoxide, come in with ethyl bromide, do your Williamson ether synthesis. These electrons here, backside attack, kick that off, boom, you just made your compound. You proposed a synthesis by working backwards, retrosynthetic approach. We'll do more examples. There's several in the workbook to work. Explain why the Williamson ether synthesis is not logical, shown there. Looks like this product is reacting with KOH and then ethyl bromide to give this ether here. What's wrong with this? One equivalent of base. Which is more acidic? Carboxylic acid or the phenol? Yeah, KOH is going to react with this H, leave that behind. I'm not going to finish it up. You're going to make anion here. Then maybe this anion could attack here, and you could get an ester. This is more acidic. The base is going to deprotonate the more acidic side. Now maybe if you use true equivalents, you could deprotonate both, but it just says one equivalent. Carboxylic acid is more acidic than phenols. Thioethers below. Same chemistry. Exact same. Sulfur is actually, SH is actually more acidic than OH. Where did we leave off? We did the first one. How about the second one? Leaving ethers with HX. First thing is to protonate the oxygen. We can do that. I'm not going to do mechanistic step. At this point, the oxygen can theoretically, well, it's going to be a leaving group. It can leave the carbon over here, or it can leave the carbon on the right. You have a choice. What mechanism do you want to do? Do we have a tertiary site available? What is this? Secondary. And what is that? Then methyl. Primary. Do we have a tertiary site available? No. And we also don't have any resonance. I mean, if this cation formed, would it be resonance stabilized? No. There's nothing going on there. So what mechanism do you want to do? SN2, right? That's what it says up there. If no tertiary site present, go SN2. If there's none present, SN2. So we got a Br minus, and we want to do an SN2. So where is it going to attack? Is it going to attack the left carbon or the right? It will attack the right, kick that off. What do you get? Show the products. Good old SN2. That is a methyl out there. We're going to get a CH3 with a Br now bonded. And what was the leaving group? The leaving group is going to be that's your LG. Right? You would cleave this ether into methyl bromide plus isopropanol, 2-propanol. Major reaction of ethers is to cleave, so they don't do many other reactions, at least until we get to epoxides. Questions about that? That one up there, though, went SN1, and the bromine ended up bonded where? Over here, because it ionized and made carbocation. Down here. What's the first step? HI. Strong acid, protonate the oxygen, yeah? I minus. do you want it to do? What type of mechanism? And primary, what is this?
That's not a tetrahedral.
That's not tetrahedral. Game over. You don't do SN1 or SN2 over there. So forget about it. Boom. Kick it off. What do you get? You get phenol plus ethyl iodide. Instead of an oxygen on that carbon, what's on the carbon now? Iodine's on that carbon now. We just did a substitution. Replacement. Replacement. It's not sp3. We don't do either SN1 or SN2 there. So really, you don't have a decision to make at all. Game over. Attack here. What mechanism are we doing? SN2. You would never do an SN1 there. You can also have cyclic ethers. Chemistry is just the same. You've got an acid. Usually under acidic conditions, the first thing you always do is protonate something. Let's protonate the oxygen. You got a Cl minus. What you want to do? Do you want the oxygen to leave this carbon or the one on the right? Is this primary, secondary, tertiary? Secondary. That left, it would be a secondary carbocation. And this would be primary, right? So what do you want to do, SN1 or SN2? SN2. Which carbon do you want to attack, left or right?
Right.
Why are we attacking the right if we're doing SN2?
Primary.
Because SN2 is mainly governed by sterics. Least substituted site is going to be attacked easier. Okay? It's just the opposite of SN1. SN1, you want a more substituted site for that cation. SN2, you want less substituted site because it's governed by sterics, backside attack, intercoordinate transition state. It's sterically demanding. SN2, what does that give? Can you show the product? The leaving group leaves this carbon, but it really doesn't leave the molecule because it's connected through the ring. Now I have a chlorine attached to that carbon. This carbon has methyl and what else? OH. So the leaving group just left that carbon, but it's still connected through the ring, you see. We didn't do any chemistry here, so that should still be bold, which, whatever this is. What is this? 1, 2, 3. H in the back. What is this? S? That should still be S. Now, this can actually react again. If we react this with HCl again, what would be the product? What type of chemistry can we do? What's the first step with an acid reagent? Protonate something. What do you want to protonate? OH. I'm just going to protonate it again. I've said this already multiple times. I'm not going to show that step because that's going to take over the course of this semester like the hour. Everybody can protonate an OH? The mechanistic step? Protonate. What do you want to do now? We got a Cl minus. What do you want to do? We made this a better leaving group. We got a tetrahedral carbon. Do you want to do an SN1 or SN2? It's secondary. Now, you should probably do either. For these cleavages, we said only do SN1 if it's tertiary available. So let's go with that. Is that tertiary? No, it's secondary. I'll probably do an SN2. Do an SN2. What do we get? Here, kick off the leaving group. And we're going to get what? This carbon has a methyl and a chlorine now. We got to draw probably draw that with the chlorine there and the methyl like this. I don't know, is that right? SN2. Is that right? Stereochemistry? That's S. What is this? 1, 2, 3, H in the back. R? Yeah. Inversion? SN2 gives inversion. Basically reacting an alcohol with ACl, we did that on day 1. This can actually react with 2 equivalents of ACl to give this. If you're just asked to show 1 equivalent, it would be that. Another equivalent here. If you were asked to give this, you might say something like ACl 2 equivalents. So subsequent reaction of your alcohol is possible. How are we doing, guys? 3/4 of this should be review. The other 4th is just the nuances that we're introducing. Do the next one on your own there. Take 30 seconds, a minute to do it. At the cyclic ether, HBr. Keep this in mind. I mentioned it before we got started, but resonance will make a secondary cation just as stable as a tertiary, if not more. So don't just blindly look for primary, secondary. If the cation would be resonance, you got to say this secondary cation is going to be more like a tertiary cation. And then you got stereochemistry to consider. Potentially, if you reacted that chiral carbon. What's the first thing you want to do in a mechanistic thought? Protonate the oxygen. All right, now we got a decision. Do you want the oxygen to leave the left carbon or leave the right carbon? If it left this, what type of cation would you make? Primary, don't do that. If you racked it over here, you would only want to do SN2. If it left this carbon, what type of cation would you get? It'd be secondary, but it would have resonance with the benzene ring. And that's going to make it just as stable as tertiary, if not more. We're going to ionize from there. And if we ionize from there, what do we get? I'm going to draw the ring out so you can see the pi bonds. This cation, that's just where we ionized. We were doing this in our mind. Here's the resulting cation, primary, secondary, tertiary. It's secondary, but what? It also has resonance. How about that? Secondary plus. Or do you want to do a plus? Something. I've never done that before. Resonance, right? Can we draw resonance structures? Do we need to draw one like the windshield wiper? Resonance arrow. All my mechanism questions say using appropriate arrows. Yeah, mechanism arrows. Well, resonance arrow, more of a mechanism arrow, curved arrow. Resonance structure. Well, I'm on here, moved out there, yeah? Windshield wiper, leaving that as a cation there. Boom, boom. We can do additional resonance. Should be able to do that. Move these over, cation here, move these down, cation there. It's very resonance stabilized. It's essentially just as stable as a tertiary or more. It's going to be easily formed. It's going to kind of fit up there. The Br minus then attacks here, and we get. I'm going to draw it all out just linear here. We got 1, 2, 3, 1, 2, 3. Then here, Br is bonded there. Why does the Br not bond to this resonance structure? Because you never want to destroy your benzene ring. 3 pi bonds in the ring. Never in this class. Maybe in some advanced organic, sophisticated, but never in this class will we destroy the benzene ring. We'll always here. Gives that product. By what type of mechanism? SN1. This is a chiral carbon. What's the stereochemistry there? Bold dash what? Somebody said it. Racemic. What does racemic mean? 50-50. This cation is trigonoplanar. Planar like this piece of paper. There's the cation. Alright, there's your cation. Bromine attacks. It can either attack this side or it can attack this side. And it's basically a 50-50. If you get into advanced, you can talk about how it's really one a little bit more. I don't know how Dr. Idell taught it, but basically it's 50-50, yeah? Racemic. That means it's going to be both dashed and bold. We could draw 2 different structures, one with R, one with S. It's a mixture. What else did we want to say? What's the name for this carbon here next to the benzene ring? General name for that. Benzylic. Benzylic. Benzylic cations are very easy to form. It's probably going to go SN1. Boom, there's your predicted product. This is THF, tetrahydrofuran. If you put double bonds in, that's furan. We'll see that here in aromatic. General Mills produces lots of furan. in addition to the syrup. Because furan is made from corn products, corn byproducts. 5-carbon sugars, they can dehydrate it to furan. Then if you put 2 H's there and 2 H's here, you have tetrahydrofuran. Cyclic ether is actually a good solvent. We react this with a strong nucleophile and no H+, what's going to be the chemistry? No reaction. In all the chemistry above, what do we have to do first to get the oxygen to leave? Protonate it. If there's no H+ present, the oxygen ain't going to leave. And thus, there's really no chemistry that can take place here. THF does not react. Ethers are non-reactive under non-acidic conditions. They're non-reactive under basic conditions. Ethers are great solvents under strongly basic conditions because they're inert to basic conditions. Diethyl ether and THF are great solvents, especially under basic conditions. You've got to have H+. Until we go to the next page. When you get to epoxides, which are 3 members, the 5 is just a plain old cyclic. The 3, because it has ring strain, you don't always need H+. But for this page, you do. Epoxide chemistry. Questions on the ethers, guys? Epoxide chemistry. Epoxides are a special type of ether. They're in a ring with ring strain. Here's a little warm-up. Epoxides actually occur, you see them in biochemistry, biochemical pathways. For example, here, you're making leukotrienes that lead to asthma responses. And drugs like Singulair inhibit leukotriene synthesis. Here's some leukotrienes. They're made from arachidonic acid. Along the way, there's an epoxide formed right here. And then if that reacts with H3O+, you can get this leukotriene. Eventually, you should be able to look back at this and kind of rationalize this chemistry. Or cysteine. Cysteine has a good SH nucleophile. Y'all remember how to make epoxides? Everybody did that in Organic 1. Epoxides are routinely made from alkenes. And the alkene is reacted with what? Somebody said it. A peroxy acid. And what's the most common peroxy acid out there? MCPBA. I know my guys heard that. Everybody, Dr. Adele, Dr. Meow heard MCPBA? Yeah. Take this alkene, MCPBA, it's in your textbook, metachloroperoxybenzoic acid. Dichloromethane is just a common inert solvent. We do need to get used to seeing solvents so we don't try to use them as reactants. It doesn't do anything. Solvent doesn't do anything. If it does, it's not a solvent. We're basically going to turn this into an oxygen bond, get rid of the pi bond. But this carbon here is chiral, and so that bond to oxygen can be bold or dashed. It will be racemic. How do we know it'll be racemic? Is this optically active? Is this chiral? No, it's not optically active. MCPBA is not optically active. Dichloromethane not optically active. Nothing over here is optically active. If we did this and only got that, is that optically active? It's chiral. It should be optically active, meaning it should rotate plane polarized light. If you did this reaction and got only that, you would have a Nobel Prize. Optical activity cannot be created out of the blue. Something has to be optically active for your product to be optically active. Actually, scientists debate, where did optical activity begin? It has to be handed down. Okay? That's how we know. But see, what we do is we get racemic. Is a racemic mixture optically active? No. They cancel each other out. The product mixture is not optically active. It can't be, because nothing over here is. That's one way to think about it. You can also do the mechanism, and you can see how you get both. You need to look back at that. Here, MCPBA, diethyl ether. That's abbreviation to diethyl ether, right? It's an oxygen with 2 ethyls. We get this. Now this is not chiral. Why? Nice plane of symmetry. And so you wouldn't say that's racemic. I could draw those bold or dashed. It's the same exact molecule. Down here, MCBBA, THF. We just saw THF on the previous page. Common solvent. We would get these 2 products, and it would be racemic. Because with the methyl, it's no longer a plane of symmetry. Basically, some review of your stereochemistry. Try to include, the comprehensive stuff here. This final exam is what? There you go. There is another way to make epoxides. Alkene, what do you get with the halogen and water? What do you call this type of compound? Halohydrin. Yes. Get the halohydrin, bromonium, and then water attacks. You should review this mechanism. If you treat a halohydrin with a strong base such as sodium, you can get the epoxide. What is sodium going to do to this molecule? Sodium reacts with alcohols to give the O-. Plus what? Forms bubbles. Hydrogen gas. We looked at that last time, right? What can this O- do? Bam. An internal SN2. Kick it off. That reaction actually also works with sodium hydroxide, but you should question that. Because sodium hydroxide is not really strong enough to make the anion. So there should be a question about that. Sodium, yeah? Kind of see this? This is kind of an alternative way to make epoxides. You might say, why would this want to make this 3-membered ring? Well, it is strained, but it'll do it. Probably because it's so easy. It's like, here we go, boom. Boom, I just make the bond. It doesn't have to search it out, it's right there. And so the transition state is improved because of that just proximity. You're also driven by entropy. I mean, you're kicking off some of the molecule, entropy driven. Okay, that's kind of an alternative way to make epoxides. Reaction zone. Under acidic conditions. Under acidic conditions, reaction of epoxides is going to be just the same as we just got through with regular ethers. No difference. No difference. I could have showed this reaction on the previous page and just kept going and we would, okay? What's the first thing you want to do in this mechanism? Protonate. It's got to be your R-. The oxygen can leave this carbon or this carbon. Either way. Do you want to do SN1 or SN2? Do you see a tertiary site available? Christopher, tertiary site? That's primary, that's secondary. Would that have any resonance? No. No tertiary site? What mechanism would we want to do? SN2. Which carbon do you want to attack, left or right? Correct. Hold on, I might have to look at this. In all these reactions, there's variability. I have to remind myself what I'm asking you guys to do. Is it the same thing? Tertiary site is present, always go SN1. If tertiary, if no tertiary, it's the same thing, right? Okay. Because a while back it used to be not, and now I'm like, well, we got to just make it more definitive. At one point we had a textbook that was like, well, you can do this, you can do that, do it this way, do it that way. Here we go. This is the same as before. We're doing it right. SN2, what's the product? I have the backbone here. This carbon now has a bromine attached. Which carbon has the leaving group? This is going to leave. Electrons move on the oxygen. Where do we want to draw the oxygen? That carbon? No, not that carbon. The oxygen is now here. Here's the two carbons. The oxygen used to be bonded there. It got kicked off. It's still bonded to this one. And this is bold. There's your product. I'm trying to illustrate with my fancy chemistry illustrator. Here's the oxygen. Okay, it's bonded. The bromine comes in, just kicks this off. This bond becomes a lone pair. So this just moves up as a lone pair, and that just kind of opens up. It's still bolded. Nothing happens with that carbon. It's still bolded. We're doing chemistry of that carbon. Here's your product. Hopefully pretty straightforward. Doesn't it look just like the previous reactions with ethers? No? Do the next one. Actually, we're about out of time. May not have time to do the next one and talk to her. Let's kind of set the stage. You can do those on your own. Where are we at down below? Is that where we're at? Okay, let's make it start. What's the first thing we're going to do here? Protonate. Just keep this in mind. Or because a protonated oxygen here is a lot like this bromonium ion. And with bromonium ions, didn't we attack and open them up? It's very analogous chemistry. Except to get the oxygen to be positive, you have to protonate it. If you go back to bromoniums, it was just naturally positive because it had the two bonds. There is some different chemistry though. Here you may not do the same regiochemistry that we're saying to do here. Because with bromoniums we always attacked which carbon? Here, would it be top or bottom? Always bottom, even if, well that actually fits here. There may be some inconsistencies between how you attack, but structurally they're consistent. They both want to be opened up. Okay, let's introduce, please look ahead and do these. You can have other nucleophiles. We've only been using halogen nucleophiles, but there can be other nucleophiles. Here, this is a source of H+. What's the nucleophile here? Not a halogen, what is it? And it's also not sulfate, because never with me we would ever use sulfate or phosphate as nucleophiles. What's the nucleophile? Water. Water's going to be your nucleophile. Here, H+. Now this is aqueous, but Your nucleophile is going to be methanol there. What's the nucleophile down here? You got some problems down here. We'll talk about it. Please use the, please Dan. Please look ahead to basic conditions. Regular ethers are not reactive under basic conditions, but epoxides are because of the ring strain. We'll look at that. We'll also be moving after this to oxidation of alcohols. Look on the daily outline.
Now we can think about that.